Okay, I got cut off at the end of the last video. Let me just go back here a little bit and remind us of what we're doing. So the problem that we're looking at is a charged particle, an electron, which is accelerated from rest through this potential difference. It goes from 0 to 500 volts, starts from rest, it accelerates because there's an electric field. If there is a change in the electric potential, then there is an electric field. That electric field is pulling that negative charge from the lower voltage plate to the higher voltage plate. That happens because it's a negative charge. The positive charge would accelerate in the opposite direction. The negative charge accelerates from the low voltage to the high voltage plate, and then it escapes through a hole in this 500 volt plate, enters into a region where there's no electric field anymore, but there is a magnetic field. And we see that the velocity is initially perpendicular. Okay, the velocity of the electron is to the right. The magnetic field is coming out of the plane of the screen. That's perpendicular. We said that when you have motion of a charged particle perpendicular to a magnetic field, you'll have circular motion. So here's the circular motion that the electron undergoes. We used conservation of energy to find what the speed of the electron was when it left the region between the plates and entered the region on the right where there's a magnetic field present. And it was 1.33 times 10 to the 7 meters per second. And it makes this half revolution in 2 nanoseconds. Okay, if it makes a half revolution in 2 nanoseconds, then that means the full period for circular motion, if it was able to go in circular motion, would be twice that, right? Because 2 semicircles make a full circle. So that would be 4 nanoseconds. The frequency of the circular motion, if it were able to continue going in a circle, would be the reciprocal of the period, so this number of hertz. We have this relationship between the frequency and the magnetic field, and the charge of the particle and the mass of the particle, solving for the magnetic field, right? Just rearranging this equation. We have 2 pi times m times the frequency divided by E. We just calculated the frequency. So we're able to calculate the magnetic field, 8.5 times 10 to the minus 3 Tesla. Okay, so the very last thing is we want to know, I guess, what was the whole point of doing this question? We want to know the radius of the orbit. Okay, where do we get the radius from? Remember this equation here, I didn't label it, but we discovered earlier that the radius is mass times speed divided by magnitude of the charge and magnitude of the magnetic field. So that's the equation that we end up using. And down here, so this is where we use it. Again, we know the mass of an electron, right? That's 9.11 times 10 to the minus 31 kilograms. We knew what the speed was. We had calculated that. Magnitude of Q is just E, the elementary charge, 1.6 times 10 to the minus 19 coulombs. And the magnetic field is what we just calculated. So we make those substitutions into this expression for the radius, and out comes 8.5 millimeters. Using standard SI units, I would have had this quantity in meters, but I converted it to millimeters at the end. Okay, so that's a really nice question because it ties in with some earlier stuff with motion of charges in electric fields and connects that to motion of charges in magnetic fields as well. Okay, so you might say, who cares? Who cares? Why should I care about this? Well, here's a really interesting and extremely useful application. So anyone who's a chemistry major should take note of this. There is a device called a mass spectrometer, and a mass spectrometer is an analysis tool. Okay, so for analyzing what? Well, for analyzing chemical composition. How does it work? Okay, imagine that you have some molecule or some substance. Maybe it's a mixture of many molecules, but just think of one type of molecule. And what happens is in a mass spectrometer is those molecules are smashed to pieces. Okay, so you start with a molecule with many atoms, they're smashed to pieces, and all of the pieces that make up this molecule that form when these molecules are smashed up, they're typically charged, so they're ionic, they're ions, they have a charge, and that means they can be accelerated through a potential difference. So imagine that you accelerate these charged pieces of a smashed up molecule through this potential difference, okay? And then what happens, well, depending on the properties of those charged particles, they will have different speeds, okay? And so what do we do? Well, you can let these charged molecular pieces enter into this magnetic field region over here. And let's see, if you happen to know what the speed is, okay, and you have a little detector here, and the detector is at let's say at a fixed position. If the detector is at a fixed position, that means you know this distance d. D is the diameter of a circle, okay, so diameter would be twice the radius. So if you're detecting a piece of a molecule that goes into this detector that goes through this little hole here, that's a distance d away from the top hole, then it turns out that you can determine from this equation here, if you rearrange this equation, you can determine the ratio of the mass to the charge of that molecular piece, okay? So if you know the speed, and if you know the radius, well, you will because you know d, and you know the magnetic field, you can determine what we call the charge to mass ratio of these this molecular piece or these molecular pieces. Okay, so so give that some thought. That's a way in which you can use this setup to measure the charge to mass ratio of charged pieces of molecules that have been smashed up. Okay, so the way a mass spectrometer works in practice is something like this, but typically you'll have many charged pieces of molecules that are accelerated across this potential difference through this hole in the plate, and then you'll have some kind of position sensitive detector along here. It won't just be a little hole with a detector that detects particles that go through this hole. You have to imagine that there's some kind of position sensitive detector that will measure, that will count particles, pieces of molecules that smash into this wall here. And this isn't a very good picture down here, but this is what this is trying to illustrate is what we call a mass spectrum. And it's basically each one of these peaks is essentially telling you, the height of the peak is telling you how many molecules or pieces of molecules are going to land at a given distance along this wall here, okay? So when the peak is really high, it means that at maybe this position right here, there are a lot of pieces that land there. If you have a smaller peak here, a little bit further out, it might mean that at a larger distance, maybe down here, there are fewer pieces that land here. And this distance is related through this equation here. Remember, r is just half that distance, d, is related to the charge to mass ratio. The charge to mass ratio of what? Well, of all of the pieces of molecules that land on this detector. Okay, so give that some thought. So what this implies is that you will have what we call a mass spectrum, which is kind of a fingerprint, of the molecule. You break that molecule up, you smash it to bits, you put it through this mass spectrometer, you You record the positions, the final positions along the detector, where all those pieces end up and how many of them end up there. And these series of spectral peaks, mass spectrum peaks, basically provide a fingerprint of the molecule. Okay, so this is a way of determining what the composition of the substance you were analyzing, what it was. Of course, before you smashed it up, you have to sacrifice a little bit of the material, the substance that you're analyzing, in order to get this spectrum. But this will tell you something about molecules, the identity of the molecules that you have smashed up. Okay, I know that's a lot to digest, but I just want to make it clear that this problem that we've just worked through has a really important application in chemistry, the mass spectrometer. You can read more about that. I'm not sure if it's in the textbook, but certainly on the internet. Okay, so let's get back to something a little simpler. What happens if the velocity of the charged particle is not perpendicular to the magnetic field? If it is perpendicular, we said that the charged particle will move in circular motion. If the velocity has a non-zero component along the magnetic field, then what happens is you get a combination of circular motion and linear motion. So let's say the magnetic field is pointing in the z direction, up, as in this picture. So if you look down the z-axis, you will see the charged particle undergoing circular motion, but you're only looking in the xy plane. Along the z-axis, the molecule is moving with a constant z component to the velocity. If you put those two things together, what that tells you is the charged particle will move in a helix. Okay, so that's what's indicated here. Charged particles, most generally, when they move through magnetic fields, they tend to move in helices. The pitch of the helix is just the distance from one turn to the other, this distance here. That's completely determined, or it's partially determined, I should say, by the angle that you choose between the velocity and the magnetic field. You can choose that angle to be whatever you want. Again, if you choose it to be perpendicular, then the pitch will be zero. And if you think about what a spiral with a zero pitch is, well, that's just a circle. Okay, so circular motion is a special case of a helical motion. So that's what charged particles do, most generally in magnetic fields. One application of this is the charged particles that come from the sun through the solar wind. You may have heard of that. The solar wind is just a stream of charged particles that come from the sun and it passes by the earth. And the earth is a big magnet. And there are magnetic fields, there are magnetic fields everywhere around the earth, but there are strong magnetic fields, as it turns out, that are also present well above the atmosphere. And the charged particles that come from the sun through the solar wind are captured by the Earth's magnetic field, and they tend to move along these magnetic field lines. And they tend to move along the field lines in this sort of spiral or helical motion. And I don't have time and I don't have a good picture to illustrate it, but this is closely connected to the phenomena of the northern lights or the southern lights, the aurora borealis you may have heard of. Anyway, it has something to do with charged particles moving in helical motion along the magnetic field lines associated with the Earth's magnetic field.